Hello students, welcome back. In this video, we will continue with Form 5 Physics, Chapter 3, Electromagnetism Part. This includes electromagnetic induction, transformers, generation and transmission of electricity, experiments of electromagnetism, and SPM past year questions. First of all, electromagnetic induction is defined as the production of an electric current by the changing of a magnetic field, such as relative motion between a conductor and magnetic field lines. There are two ways to generate induced current. First is moving a straight wire quickly across a magnetic field between two flat magnets. Second is moving a permanent magnet towards one end of a solenoid. Every time the straight wire cuts across the magnetic field or the permanent magnet moves towards the solenoid, a current is induced in the coil and a deflection is observed in the sensitive galvanometer. This current is called induced current. The electromotive force that is produced is called the induced EMF. To indicate the direction of induced current in a straight line, Fleming's right-hand rule is applied. By definition, if the thumb and the first two fingers on the right hand are held at right angles to each other, with the first finger pointing in the direction of the magnetic field and the thumb in the direction of motion, then the second finger is pointing in the direction of the induced. Here is an example to test your understanding of this rule. A wire PQ is moved vertically downwards in a magnetic field. Applying Fleming's right-hand rule, the induced current will flow from P to Q. To indicate the direction of induced current in a solenoid, we are referring to Lenz's law. Lenz's law states that the direction of the induced current in a solenoid is such that its magnetic effect always opposes the change producing it. There are two situations to generate induced current in a solenoid. First is moving the magnet towards the solenoid. According to Lenz's law, induced current produces a north pole to oppose the motion of magnet coming towards the solenoid. Furthermore, when the magnet is moving away from the solenoid, induced current produces a south pole to attract the magnet moving away from it. In short, we can summarize Lenz's law for a solenoid as the table below. When they move towards each other, some polarity will be produced at the end of the solenoid as the magnet. When they move away from each other, opposite polarity as the magnet will be formed. For your information, Lenz's law satisfies the principle of conservation of energy. When the magnet or solenoid is moving against the opposing force, work is done. Therefore, mechanical energy is converted to electrical energy. To investigate the factors affecting the magnitude of induced current, Faraday's law is considered. It states that the size of the induced EMF is directly proportional to the rate at which the conductor cuts through the magnetic field lines. Therefore, the size of the induced EMF and the induced current can be increased by moving the magnet or the solenoid at a higher speed, increasing the number of turns on the solenoid, or increasing the strength of the magnetic field with a stronger magnet. For the application of electromagnetic induction, current generator is considered. Current generator functions by converting mechanical energy into electrical energy. Moreover, it works based on electromagnetic induction and uses the Fleming's right-hand rule. Current generator is divided into direct current, DC, generator, and alternate current, AC, generator. For a DC generator, commutator reverses the connections of the coil with the external circuit every half cycle, so the current in the outside circuit always flows in the same direction. The induced current varies from a maximum to zero and it flows in one direction only. Hence, the induced current is called a direct current. For an AC generator, the two ends of the coil are connected by two slip rings which rotate with the coil. Each slip ring is always in contact with the same carbon brush. Based on the diagram above, output current generated is an alternating current. For an AC generator, the two ends of the coil are connected by two slip rings which rotate with the coil. Each slip ring is always in contact with the same carbon brush. Based on the diagram above, output current generated is an alternating current because the current changes direction in the external circuit. If we assume the current flow from P to Q is positive and the current flow from Q to P is negative, therefore the current changes in magnitude and direction after every half rotation. Here is the comparison of direct current and alternating current. Direct current flows in one direction only and can be constant or changes with time. For AC current, furthermore, a direct current can flow through a resistor but cannot flow through a capacitor. However, an alternating current can flow through both resistor and capacitor. The next subtopic is transformer. So basically, a transformer is an electrical device which increases or decreases an alternating voltage. The structure of a simple transformer consists of two coils of wire rounded around separately on a laminated soft iron core. The coil connected to the input voltage is called the primary coil. The coil connected to the output voltage is called the secondary coil. The purpose of the common iron core is to provide a magnetic field linkage in the secondary coil. To describe the operating principle of a simple transformer, it works on electromagnetic induction. When an AC voltage, Vp, is applied to the primary coil of a transformer, an alternating current flows through the coil. The soft iron core is magnetized in one way and then the other. This means the magnetic flux linkage in the secondary coil is constantly changing. An alternating EMF is induced across it to produce an AC voltage Vs in the secondary coil, and AC current flows through the second coil. The frequency of the secondary voltage Vs is the same as that of the primary, but the magnitude of the secondary voltage Vs depends on the ratio of the number of turns of the primary and secondary coils. The reason why the transformer does not work with the DC power supply is because the current will only be induced in the secondary coil when there is a changing magnetic flux due to a changing primary current. A DC power supply gives a constant current in the primary circuit. This means that a constant direct current whose magnitude and direction is constant does not create a changing magnetic flux in the secondary coil. Therefore, electromagnetic induction does not take place. Now we will investigate the relationship between the number of turns in a coil with the voltage in a transformer. According to Faraday's law, the more the number of turns in a coil, the higher the induced voltage. The formula as given in this figure is very useful in calculating the induced voltage and determining the types of transformers. There are two types of transformers, which are the step-up transformer and the step-down transformer. For a step-up transformer, the NS is greater than NP, and the VS is greater than VP. For a step-down transformer, the NS is lower than NP, and the VS is lower than VP. Next, we will look at the relationship between output power and input power of an ideal transformer. Theoretically, a transformer transfers electrical power from the primary circuit to the secondary circuit. The primary circuit of a transformer receives power at a certain voltage from the AC power supply, and the transformer delivers this power at another voltage to an electrical device connected to the secondary circuit. In an ideal transformer, there is no energy loss during the process of transforming the voltage, and this is clearly shown. However, in a real transformer, some energy is lost in the transformer, especially in the form of heat. The output power is always less than the input power if we are not stepping up or down the primary voltage. Therefore, the efficiency of the transformer is less than 100%. To investigate the efficiency of a transformer, this formula below is created. The power loss is due to heating of coils, eddy currents in the iron core, magnetization and demagnetization of core, leakage of magnetic flux. Here is a table of ways to solve the power losses. To reduce the heat energy loss in the coils, thick copper wires can be used to make the coils. This is because the resistance will reduce as the wire is thicker. Furthermore, the eddy current in an iron core can induce heat loss during the transmission. To reduce the eddy current, laminated cores can be used. During the magnetization and demagnetization of iron core, work must be done to change the magnitude and direction of the magnetic field in the core, which contributes to energy loss. To solve this problem, soft iron cores can be used as it is easily magnetized and demagnetized. For the leakage of magnetic field, we can reduce the distance between the primary and secondary coils by winding the secondary coil on top of the primary coil. Moving on to the last part of this chapter is generation and transmission of electricity. So, what is electricity? Electricity is generated in power stations, transmitted through long-distance cables, then distributed to customers. Here is a list of sources of energy used to generate electricity. There are two categories of energy. One is renewable energy and the other one is non-renewable energy. Renewable energy is energy source that is continuously replaced and will not run out. For non-renewable energy, they can't be replaced once it is used up. The examples of renewable energy are solar energy, wind energy, hydropower energy, biomass energy, tidal energy, and geothermal energy. Fossil fuels, coal, natural gas, and nuclear are considered non-renewable energy. The basic principle in generating electricity is using generators. A generator has a huge magnet that is turned by a turbine. As the magnet turns inside a coil of wire, electricity is provided by electromagnetic induction. All sources of energy that we mentioned previously are used to turn turbines to generate electricity. Firstly, we will look on a coal-fired power station. Coal is burnt to release heat energy that will produce high-pressured steam. The steam produced is used to drive the generators to produce electricity. The energy changes from chemical energy to heat energy to kinetic energy and finally to electric energy. Next is a gas-fired power station. The burning of natural gas produces high-pressured steam that is used to drive turbines. The energy changes from chemical energy to heat energy to kinetic energy and eventually to electric energy. For a hydroelectric power station, a huge dam is built across rivers to contain water. When the water in the dam is allowed to flow down to a lower level, the kinetic energy of the moving water is used to drive water turbines, therefore the energy changes from potential energy to kinetic energy to electric energy. Furthermore, a nuclear power station applies energy from nuclear fission to produce high-pressured steam in driving the turbines. The energy changes from nuclear energy to heat energy to kinetic energy to electric energy. For a biomass power station, rotting plants and agricultural waste such as oil palm kernels and household sewage are used to produce methane gas and alcohol. This is because the heat energy from the burning of biomass is used to generate electricity. Moreover, solar devices use solar energy which originates from the sun. For instance, solar panels use sun energy to generate heat energy to heat water at home, and solar cells use sun energy to generate small electrical energy to power calculators. For a wind power station, high-speed wind can be used to turn blades of large windmills, which will in turn drive generators to produce electricity. In the transmission of electricity, electrical energy is transferred from power station to consumer using long transmission cables or power lines. Electrical energy is transmitted at a high voltage and using alternating current. A step-up transformer which increases the voltage to as high as 110,000 or 132,000 volts is used, and a step-down transformer functions to decrease the voltage before being delivered to consumers. For your information, the long thick cables used as transmission lines are made of copper or. Why do we need to step up and down the voltage in the way of transmission? This is to reduce the power loss in cables. Therefore, the power loss can be reduced by reducing the resistance of the cables and reducing the current in the cables. In order to reduce the resistance of the cables, a thick cable is used such as copper or aluminum. However, thick cables are very expensive to install and will be too heavy to be supported securely. Therefore, the loss of power in the transmission of electricity is reduced by lowering the current in the cables. The power to be transmitted by the cables is P equals VI, where I is equal to the current in the cables and V is the voltage of the. Based on the previous formula, the current in the cables is inversely proportional to the voltage of the cables of a certain value of power transmission. When power is transmitted at a lower voltage, the current in the cables is large. The greater the current in the cables, the larger the power loss. Now we will go through what is the National Grid Network. National Grid Network is a network system of high-voltage cables which connects all the power stations in the country to the consumer. Electricity is generated at 25 kilovolts at the power station. It is then stepped up in a transformer to 132 kilovolts before it is sent to the grid network. The purpose of increasing the voltage to 132 kilovolts is to lower the current flowing through and thus reducing the power loss during transmission. The high voltage in the grid is subsequently reduced by substation transformers for distribution to local users. Heavy industries will be supplied with power at 33 kilovolts. Light industries will be supplied with power at 11 kilovolts. Offices will be supplied with power at 415 volts, while domestic users will be supplied with power at 240 volts. There are several importance to the national grid network. Firstly, the cost of generation of electricity is reduced because high voltage transmissions reduce the current flowing through the cables and hence reduces the power loss in the cables. Furthermore, power stations in areas where the demand is low can supply electricity to areas where the demand is high. If a particular station breaks down or is in shutdown for maintenance work, the other stations can supply electrical energy to the affected area. Moreover, the grid network also enables less efficient stations to be shut down at off-peak periods, thereby reducing the overall cost of generation and transmission. Lastly, the national grid network allows power stations to be located outside city limits so that the air and environmental pollution can be reduced. Let's have a look on some transmission issues of the national grid network. In this table, we have explanations on using AC current, high voltage, aluminum cables, metal support of pylon, and why the cables are hanging overhead. For the importance of renewable energy, the very first reason is because of non-renewable sources of energy, such as crude oil, coal, and natural gases, are fast depleting. Alternatives must be found to replace such sources to ensure continuous supply of power in the future. Renewable energy sources are those which originate from the sun or the earth and will last as long as the solar system itself. These sources do not pollute the environment as well. For instance, from the sun we have solar panels, solar cells, biomass, wind and wave energy, and hydroelectric power. From the earth we have geothermal energy and energy from the tides. Here is a list of advantages and disadvantages of using various sources to generate electricity on the environment. Even though our world is encouraging the use of renewable energy, there are still some limitations on these sources, such as the lack of space, high costs, and high risk of accidents. One of the experiments in this chapter is step-up and step-down transformers experiment. The objective of this experiment is to help us understand clearly the function of step-up and step-down transformers. Based on the results, the voltage at secondary circuit of step-up transformer is higher than the primary voltage and the brightness of the bulb is greater. For a step-down transformer, the brightness and voltage readings are lower than the values from the primary circuit, as the primary voltage is reduced. As a conclusion, the greater the number of turns of the secondary coil, the greater the output voltage. Here are a few SPM past year questions with the solution provided. Let's try to concrete your understanding on this chapter. Thank you for your patience and see you soon.